Christian Johansson, who will speak on a categorical p-adic local Langlands correspondence for GL2.
Thank you very much for the introduction, and thanks to the organizers for being here. Great pleasure. Okay, so the thing I want to talk about today is a categorical formulation of the p-adic local Langlands correspondence for GL2QP, and this is joint with James Newton and Carl Wang-Eriksson. So before I forget, my prime this talk is going to be greater than or equal to 5, and some of the things I say will not be true for p equals 2 and 3. All right, so what's the goal? So the goal here, it said, is to give a formulation of the p-adic local Langlands for GL2QP of the form of the very rough form, sort of on the one hand, we have locally finite length. Smooth representations, GL2QP. And a suitable category of those will embed fully faithfully into some category of, roughly speaking, quasi-coherent sheaves. On a stack of two-dimensional continuous representations of, can I fit this? Maybe. Of the absolute Gallagher group. That's the vague goal, and I'm going to spend sort of the first half of the talk explaining this side and then explaining that side in more detail. So we came to this question in a rather roundabout way. We started with questions about sort of overconvergent eigenforms on SL2, SL2Q, and in particular the question that was mentioned in Eugen's talk earlier about the existence of non-classical eigenforms whose system of Hecke eigenvalues is classical. Particular sort of, in the case of SL2, this is related to endoscopic phenomenon, and we wanted to try and understand this in terms of some kind of p-adic local Langlands SL2 and families, and seeing how those things fit together. And then we were kind of led to ask ourselves, well, what's p-adic local Langlands for SL2QP? Doing calculations, we kind of came back to wanting to give a different formulation for GL2Q. All right, so let me start by explaining this side of the picture. On the GL2QP side, I'll have, first of all, I'll write G just for GL2QP. Inside here, I'll have B, my upper triangular Borel, as usual. I'll have T, the diagonal torus. And I guess I'll also have Z being the center. All right, and I'm going to fix, well, as my coefficients, I'm going to fix a large finite extension of QP, but really I'm gonna just. I'm gonna pretend that this is, well, I don't know, QP bar or whatever. I don't want to keep making remarks about the difference between absolutely irreducible and irreducible representations and this kind of thing. So just pretend that this is large enough. And then I'll write O for the ring of integers, and I'll need it, but I will be a uniform answer.
Sorry, could I interrupt briefly?
Sure.
About that L. So that L or Q bar, that doesn't affect this response, this embeddings.
Sorry?
That doesn't affect the embedding, the choice of coefficients.
The choice of coefficients. Well, I guess technically there will be for each choice of coefficients, there'll be an embedding. Yes, they'll be compatible with some sort of extension of scalars.
So it does appear on that side as well.
It does appear on both. It does appear on both sides. I mean, I'll get into it, but I mean, there will be questions about sort of which things are, which representations are irreducible but not absolutely irreducible. Galois invariance and things like this. But I'm going to sweep that under the rug completely. So I'm also going to fix a central character. So data be a smooth character. It's going to be my fixed central character throughout this. And in general, I'll, whenever I have a character QP cross, smooth or sufficiently nice, I'll conflate it with the corresponding Galois character using local clustering theory. So.
Can you comment on why smooth is a natural assumption in this context? And wouldn't continuous be somehow more?
All of these representations are going to be smooth. So their central characters will be smooth.
Then this is not what most people would call a p-adic local Langlands correspondence, surely.
Version coefficient. No, but it's version coefficient version. I guess.
That's got a limit. Again.
Yes, there will not be Banach spaces appearing. If that's the. All right. So then I guess I want to introduce the following ring, defined by Johansson, which you can define by picking any compact open subgroup really, but right. We take the subalgebra of favorite compact open subgroup, go to ZP, and then you tensor it with a group ring, and then you can check that this has an induced ring structure as well, which doesn't depend on your choice of compact open. And there are probably different ways that you can sort of describe this. So this is a pleasant device working with. It's not Noetherian though, so the ring is a little bit nasty. And I'll also need, because we're working with a fixed central character, I'll need the quotient where I impose this condition. The two-sided ideal generated by these things. All right. Okay, so now I can start writing down some categories. So as the sort of biggest category I'll consider is just going to be the category of left modules of this ring that I just read. And inside this, I'll have the category of smooth representations, central character zeta of G. So let me remind you here that so smooth smooth reps of G, coefficients in O. And this means that they're torsion. So this here means, so if I have a capital V thing in here, then by definition, for all V and V, first of all, everything is torsion. So you're killed by some power of the uniformizer. And the stabilizer is open. So the second condition is the usual one. You have the smooth representations, and this is something that you additionally impose in the setting. And then we get to the category that I was alluding to down here, which is the category of locally finite length representations, or equivalently locally admissible representations. So locally here, meaning that it's a union of admissible representations, or equivalently in this particular case, it's a union of finite length representations. Okay, so these are my categories. Any questions on this before I proceed? So the thing we're going to need for this category here is the structure theory that was developed by Pascal. I don't have the excuse of latex. Remember. So the first thing that comes into this is if I look at the set of all irreducible representations, so isomorphism, I guess. Then I can define an equivalence relation on this by, well, one sort of cheap way of saying it is that first I take the relation, which is just saying that a pi and a sigma in here are related. If they have a non-zero X group between them, right? And then I'm going to let tilde just be the equivalence relation. Generated by this relation. So two things are related. If I can find a sort of chain of extensions one way or the other, but between irreducibles. So the equivalence classes here. Equivalence classes are typically called blocks. And they look like the following. So let's see. So in this situation, we're going to have four different types. So our blocks, which are singletons, where pi is a so-called supersingular representation. Of GL2QP, so irreducibles that do not show up in as a subquotient of a principal series. And then we have blocks of principal series. So if I take two characters, I should. So let's see. Two characters, chi1 and chi2, then there are two principal series I can form. So here, omega corresponds to the mod p cyclotomic character. And for this particular block, I impose the condition that the two characters I've taken, the ratio is not trivial, and it's not plus minus the cyclotomic. Second type of block. Third type is just what happens when the characters are equal. In that case, you just have a single representation. And finally, there's the most complicated one. Is what happens when you have the other ratio. So in that case, you'll have chi, well, it's chi can finite dimensional representation. You'll have the Steinberg boosted by chi, and you'll have the induced representation, which I was going to say. Which looks like this. When p is at least 5, these are the four types of things that you can get. And so they correspond to Galois representations. So this was sort of price, I guess, mod p semi-simple local Langlands. One of the first signs of a p-adic local Langlands is that you can match these up with 2D two-dimensional semi-simple Galois representations, where sort of these correspond to the supersingulars correspond to the irreducibles. This one corresponds to chi1 plus chi2. And this one corresponds to chi, and this one is chi times cyclo plus chi. So I'll write So I'll write row bar B. Semi-simple. The Galois, and I guess I'll want to shorten my notation. For the Galois groups, I'll just call it gamma. Corresponding. To B.
Could I ask a really stupid question? So on the right side, there are no blocks, I guess, right? On the Galois side,
Side.
the Galois side.
So there are components of the moduli space.
They correspond
They
to.
correspond to blocks. Yeah,
Okay.
I'm gonna get this. I'm gonna get there very soon. Yeah. Alright. So the blocks give you a decomposition of this category as a product. Subcategories where this is the subcategory. Full subcategory such that these objects have sort of all irreducible subquotients. Quotients in this block B. The point is basically here that, I mean, the blocks are defined in such a way that there can be no extension between things that are in different blocks. And so the category just breaks up into subcategories which have no interaction between, no extensions between them at all. All the interesting information somehow happens within these categories. Yes.
Just a question. So for the blocks you're describing here, these are all mod P or these are all just.
The representations are all mod P.
Okay, so they're all mod, okay.
Yeah. So
It's like general torsion.
well, I mean, because we have torsion, anything that's irreducible will have to be
Will also have to be mod P. Okay, I see.
Is this a finite product?
What's your coefficients?
Yeah, I was gonna say my coefficient. I guess that if I fix coefficients, then I'm gonna say if I fix coefficients, I guess they're only finitely many. I'm not gonna be able to work this out in front of the board. And so what's the point? Well, the further point is that these things can also be described more concretely as modular category. So it's really the meat of schematic work. So for this, that's the following. So I'm gonna let phi b be the sum of all the irreducibles that lie in this block.
So, sorry, Christian,
Yes.
we'll dwell on this point a bit longer.
I probably can't, but maybe you can. Yeah.
Let's say that your coefficients have residue field K, the quadratic extension of K. Then you take a character chi1, chi2, which is valued in the quadratic extension subfield. So that would give you an irreducible representation, say, with coefficients in that quadratic extension. And then if you just restrict the scalars to K, then it's probably still irreducible as a K GL2QP module. But where would that fit?
This is why he said to pretend that he's working over. Bar.
Okay, but this is clearly where you can't pretend and you have to say what's going on.
But no, I mean, yes, if we're going to have to be careful about this point, then no, not every block looks like the one I just described. The ones that contain absolutely reducible representations look like this, and then there are blocks that don't, and they come from, yeah, they'll look like one of these blocks after I extend the scalar, but then there'll be some Galois.
It is an infinite product, even though the coefficients are finite.
But yeah, so you have to take these into account as well. But you can sort of, you can play a game where you extend scalars and then sort of look at the action of Galois on both sides and sort of reduce every question about such a block to a question about one of these blocks by extending scalars.
And then if it is an infinite product, is product the right word, or?
I think product is the right word. Yeah. So things in here, objects are direct sums. But if I remember my category theory right, this means categorical terms is a product of categories. Someone can correct me if I manage to get this wrong.
Oh, sorry, just to be sure I understood. Sorry about that. If we fix coefficients, this looks finite, but if we fix coefficients, this isn't the right description. That was the.
Coefficients, this is not the right description. No. You have to allow for things that look like this after you extend scalars, but does not look like this.
The person who raised this question, can I suggest we not discuss it any further?
Okay, so 5B here. Into choose an injective envelope where it has enough injectives. Then I'm also going to consider its Pontryagin dual, although I won't be saying too much about where this thing lives. So, but now we're sort of, this is the kind of object, or at least summons of this is the kind of object that showed up in the talks about the Gauss conjecture. Very quick. Then I'll define a ring, which is a compact ring. You can either describe as the endomorphism, so this PB in a suitable category, or if you just want to stick with the category that down on the board, it's the opposite of the endomorphism, so this injective envelope IB. And then the sort of general theory of these types of categories give you that block here is equivalent to the category of discrete left modules of this compact ring. And the functor, one way to write down the functor is to consider this PB over the completed group ring thing that I wrote down. What's So what Pascunas did was to compute these rings explicitly. So in particular, he proved that the center is equal to RB, which is the universal pseudo-deformation ring. Of the trace of this mod P representation rho B with determinant. It's a fixed determinant, corresponds to my central character. And EB is finite as a module. Over this RB. And then you can describe it in each case. Basically, it looks like some kind of generalized matrix algebra over these rings. Rather pleasant. It's also closed to what's called the universal Cayley-Hamilton algebra, or this representation of it. So this later, but I can write it down. So the universal Cayley-Hamilton algebra given a particular pseudo-deformation ring is what you get by taking the completed group ring for the Galois group, and then you mod out by requiring that the characteristic polynomial is the one that it has to be. So G. G gamma. Maybe I should close this. Right. So in particular, these two rings are equal in the cases. Well, in those two cases, these two rings are isomorphic. In this case, EB is just RB. And in this final fourth case here, this thing has this as a sort of, roughly speaking, as a subring, but it's a bit more. Okay, so let me now move over to the Galois side. Hopefully requires a bit less of a pre-report. So in this case, you can define a moduli stack, which, to answer Minnie's question, is disjoint union like this, living over the disjoint union of the pseudo-deformation spaces. So this is the moduli stack. Of continuous 2D representations of gamma over the kind of test objects that you can take here are the sort of formally finite type O-algebras. So this is a thing you can basically write down and represent without trouble. And this is just a map that takes the representation to its corresponding pseudo representation, and the pseudo representation space breaks up as follows.
I think yesterday, what is the coefficients of the pseudo representation?
But it was the coefficients. So the coefficients of these representations are formally finite type O algebras. So things that look like things that are quotients of sort of power series rings, and then you allow some restricted power series.
These XB.
Right. So if you ignore this for the time being, I'm claiming that every pseudo representation, so every Galois representation can be mapped to a pseudo representation. So this is just a map from the moduli of representations to the moduli of pseudo representations. The moduli of pseudo representations proved by Genevier to split into the disjoint union of the deformation spaces for each of the sort of semi-simple ones mod P. And so these components are just
See, okay.
parts of these things. Okay, so when you're doing,
So I guess you're implicitly using here that the blocks you had before actually biject with the
yes,
semi-simple mod P.
absolutely. Right. So you can sort of create versions of these which are algebraic stocks. So it's done by. This is, so you have sort of algebraizations. Are now general so algebraic stacks that live over the spectrum of these pseudo deformation rings, and each one of them is finite. Sort of, it's an algebraic stack of finite type over RB. So these are not very scary objects. So they each one of them look like an affine scheme, modulo reductive group. Like this, where this SP will be finite type over RB. And this thing is, I'm going to say, it's either Z mod 2 or GM, or in the worst possible scenario, it's SL2. And you can really write these down very explicitly. These things are defined in terms of representations of these Cayley-Hamilton algebra. So in particular, thing I'm looking for sort of is categories of quasi-coherent sheaves. So a quasi-coherent sheaf on this XP, you can just think of as an equivariant. Sorry?
Trivially on the rings. Yeah, on the rings. Because it's more semi-linear representation.
Sorry?
More like semi-linear representation.
More like semi-linear representations, yeah. Okay. I guess I want to take that into. Yeah, equivariant with respect to the action on SB. All right, but then I can state the paper. So we're going to do this sort of block by block, which perhaps is not the most invariant formulation, but so for all blocks there exist, and I'll write out co-limit preserving these. Like functor, which, so I'll take the source of this can be made to be all of these, all modules for these modules for this ring, going into quasi-coherent sheaves on XP, and here I'll be a little bit lazy here. So this means the unbounded derived category. Here I'll just sort of do as they do in geometric Langlands and let this denote the unbounded derived category of quasi-coherent sheaves. So that's just a functor. Claims then that this, when you dissect it a little bit further, it induces an embedding. Of the thing that I wanted. So of this particular block, the unbounded derived category of the block into, and here you have to sort of mess around a little bit. In order to actually get an embedding, you have to mess around a little bit of the structure of this. You have to consider this sort of in the category of coherent sheaves. And if you really want to be detailed here, you can write a little m here, where m here is the maximal ideal for this ring. So all of these will be sort of m infinity torsion. Which in some sense, just to state why one might care about this, means that they really sort of, they can really be thought of as sheaves on this thing. So this thing you can recover from the algebraization by taking an m-adic completion essentially, and this just tells you that they really live on this. So this is exact, I said, in the sense of triangulated categories and in the sense of stable infinity categories, if you like. So this here, you should probably give this a name. So it is T exact, at least on here. For blocks 1, 2, and 3, but not 4. So in particular, you can compute this for all irreducibles. You can see that this lives in homological degree. which is 0 if dimension of pi is infinite, and 1 if the dimension of pi is finite, or pi irreducible.
Can we split FB to a different block B prime if it's 0?
Yeah, it's 0. So I mean, you can take the product of these functors and get something that's invariant under the block, but to construct them, you sort of go block by block. Okay, so very briefly, what's the idea of proof here? So the only reason really that I mentioned that it was co-limit preserving here is that such functors you should typically think of as being tensor products. So sort of, if you like, Morita, some version of the sort of philosophy of Morita theory will tell you that every such functor should be thought of as a tensor product with a sort of bimodule. So you have to cook up this bimodule, whatever this means. So you need a sheaf of right. Yes. A sheaf of right modules on this XP. Then your functor would just be tensoring. So how are you going to cook this up? Well, the key here is to find an object here, which turns out to be maximal Cohen-Macaulay and a genuine sheaf. Such that if you take the arhams of this thing with itself, you just get back EB. So meaning that the homs, so the endomorphisms of this is EB, and the self and the X dies between VB and itself is a 0 for all I greater than 0. Then I can cook up this sheaf by essentially taking now this sheaf here, dualizing it, and tensoring it over EB with this EB thing. This is now a sheaf because this is, and it's a right module for this ring because that is. And then the functor is given by sending sigma to taking the dry tensor product. And the way we produce these things is somewhat dumb. So we write down objects and we verify more or less by explicit computations on both sides that they satisfy this thing. In particular, sort of showing that the endomorphism ring is EB is the most annoying part of this.
So is VB tilde supposed to be the image of this PB under your functor or something like that?
Well, so PB is not, strictly speaking, in my category.
Oh, it's duals.
It's dual as well. I mean, I was going to say, not quite as simple as that. So I don't know exactly what the image is, because I mean, you're tensoring this, but I think this thing with IB itself, and I mean, you're getting some kind of sort of the EB module that corresponds to IB is some rather nasty thing. I was going to say, maybe not that nasty, but it's some sort of some sort of discrete module cook up using this. I don't know if it's related to the Pontryagin dual or something. I don't know, but somehow it's not.
Okay, so
I don't know.
so my
Can't
one,
tell.
yes, is probably not right.
Not quite. No, it's not quite as simple as that somehow. It's somehow more. It seems to, at least to us, sort of easier to understand what this functor is doing by looking at what it does to irreducibles than looking at what it does to generate. And in some sense, these categories are generated by irreducibles in the sense that everything is built from irreducibles by taking extensions and then taking. So you can actually get a good control.
Where you insist that it's maximal convex.
I don't.
Someone understands that you kind of
I mean,
not really needed for the technique, right?
no. It's. I just wrote this because that happens to be the case. We didn't go looking for something that was more common quality, but sort of given that you want the higher self X to vanish, like the better. Yeah, the closer this is to being a vector bundle, the easier your job is going to be. So a lot of the time, but at least in this case, 2 and 3, this is really the sort of universal Galois representation, the vector bundle corresponding. Right. Let me just write. In the same way that EB was closely related to the Cayley-Hamilton algebra, this thing is closely related to the universal Galois. Okay. Okay, so let me finish my last few minutes by very, very briefly stating two applications.
Could I interrupt with one question?
Yeah, sure.
I presume you don't know much about the image of the functor?
I mean, I can't give you a character. I don't think I have a characterization saying that it's exactly these things. But everything is so explicit that you can kind of see. You can see a lot of what you get in the image just by sort of from the computations that you do. So
Maybe this is outlandish, but do you see any of these kind of support conditions of geometric Langlands type coming up?
these sort of nilpotent, these seem to be vacuous in this case. Everything has this automatic, right? It's only in this fourth case that you actually have a singularity. And there they seem to be automatic. Okay. So the first one I want to state is just the relation between this construction and the Montreal functor of Gomez. So all theorems in p-adic Langlands more or less are proved using Gomez's Montreal factor. So what's the relation? So the theorem here is that if you take a representation, answer it, and you look at the global sections of this thing, take the functor, you tensor it with the universal Galois representation. This now gives you something which has a gamma action.
I is sigma, I think.
Pi is sigma. Thank you. Then this recovers Montreal functor. Which here I'll take it to go from this block to discrete gamma modules. Oh, you write down R gamma to start with, and then you prove that this is Tx, and then you prove that it's T exact. So yeah, you write down something on the derived category first, and then you prove that this is T exact. So this one, the thing that you get after this part. Yeah, looking in degree six.
Be exact for these like blocks 4 or
So there's T exact for all in all situations in this case. So sort of the Montreal functor kills finite dimensional representations in this one.
Sorry, so you said the functor, what did you call it, FB or something? The original functor is not T exact for block 4.
Yes.
But when you do this whole R gamma thing, it becomes T exact. for
When you do this, yeah, when you do this thing, it becomes T exact. It kills, in particular, it kills the finite dimensional representations, which are really the obstruction to being.
I see, that's what you said, I see.
All right. And I was going to finish with an application to eigenvarieties, but I think I'm out of time, so I'll stop here. Thank you.
Thank you very much for this very. Are there any questions or comments? Hey, Joel?
could you say something about applications that I can write?
That would be my question.
Okay, good. The freedom to say something without without being as explicit and punished for it as well. So the application is basically a formula that's sort of somewhat similar in spirit to what Huygens had, but a little bit different. And not using any stacks of phi gamma. So let me just write down a formula, and then I'll try and explain terms. So it's really a part of a sort of a local global theorem, local global comparison theorem. So on the one hand, I'm going to have some homology, and on the other hand, it's going to be a nightmare, but let me write it down anyway. Everything maybe I'll need shift. Okay, so what have I done? This here is not first of all, for this I want to work we wrote this down for PGL2 of the Q. So everything is sort of PGL2 modular curves, looks like this. This thing is not a level and modular curve. It's a slight variation of that. It's sort of a p-arithmetic locally symmetric space where you throw in, you form your usual thing, but you throw in the Brouwer-Tietz tree. At P, this is p-arithmetic. It's p-arithmetic homology with coefficients in any, well, in this case, it's going to be a module for this group ring. And the claim is that this is isomorphic to something that you now have on the Galois side. So I'm fixing some global R bar, what the Galois representation with some properties. That's in the 6 open paper. It comes with some sort of global to local map of Galois stacks, if you like. And then I take this thing, I apply my functor, do the exceptional pullback along here, and maybe I do some shift. I tensor with the universal Galois representation on here. And I take, well, homology. Doing this with homological conventions. Yeah, so this is the formula. Has some similarities with things that I wrote down. In particular, it's important here as well that you consider the stackiness of objects. And if you want to make an application to eigenvarieties, then you have to put a particular system of coefficients here. And that system of coefficients is basically you take this t hat. Maybe now it's for the sort of object. Let's see. Is this what I want? Well, okay. It's the global sections. You take the global sections of this and you induce it back up. You hit it with this, and what comes out here is the global sections of a coherent sheaf on the eigencurve as defined by Guillaume-Tarak. And then you have a formula which do something. And there should be sort of essentially, I think any cohomological, any eigenvariety that's constructed using singular cohomology, you should be able to write the global sections of the coherent sheaf on it as a p-arithmetic homology group. And you plug it in and you get some formula.
Does this formula hold for non-Eisenstein R bar or?
No, I mean, we certainly haven't proved that.
So this is like a wait.
There are lots of assumptions on R bar, and this is not the strongest possible theorem you can hope to prove. But yeah, so the assumptions on R bar are essentially the same ones as you have in the 6th author paper in the local global statement. So the sort of minimal ramification outside of P, so on. No vexing primes. I don't know. Yeah.
Does this categorical formulation of the p-adic local Langlands correspondence give you any insight? I mean, what one can expect for GL2 or the finite extension of QP?
Well, so what I didn't mention is that there's a more high-powered version of this picture that's being developed by Matt Hemerton and Toby G and Andrea Dotto, where instead of using the Galois stacks, you're using the Hemerton G stack. And in this case, you can hope to you hope to have a sort of a fully faithfulness on the whole category smooth representations. And I think that so I don't have a conjecture of what this picture looks like when you extend it.
Mhm.
They do. I mean, I think something like there should still be a sort of a version of this, I believe, but I'm not exactly sure what categories should be, or what the source category should be in particular.
A quick question, David. I mean,
You were careful to say that this was a fully faithful embedding. Is there a reason why that you know that it's not surjective?
Well, you can write down the puncture is explicit enough that I can just see that there are lots of things that. Short, if the short.
Short answer is fine, a long answer can be discussed, I mean.
I can say that the structure sheet is never in the image, for example. Just as a.
It hits all the irreducibles.
Sorry.
It somehow hits all the irreducible objects in some sense.
Well, it depends on what you mean by that, but yeah.
Right, okay, can we postpone any further questions to the 8 minutes that we have until the next talk? Thanks.